Every modern large language model shares the exact same objective: to look at a sequence of text and predict the next single token. The acronym GPT stands for Generative Pre-trained Transformer, and to generate just one new word, a transformer performs computation on a scale that defies human intuition. Take GPT-3 as a baseline. It contains 175 billion learned parameters. These 175 billion numbers form 28,000 matrices across 8 categories. To understand this, separate the static architecture from the flowing data. The blue and red matrices are the weights, the model's fixed brains. The gray blocks flowing through are the input text. The entire system boils down to sequential matrix vector multiplications. We will eventually look at the hidden layers in the middle of this pipeline, but first we need to map the outer boundaries. We need to see exactly how discrete words become continuous geometry at the start, and how that geometry collapses back into text at the very end. There is no magic happening inside these networks. It is a strict mathematical pipeline that translates human language into linear algebra. The first constraint of any neural network is that it cannot read raw text. Every piece of input data must be formatted as an array of real numbers. So the input text is broken down into small pieces called tokens. The model draws these from a predefined vocabulary containing roughly 50,000 possible pieces. This brings us to the first pile of weights in the network, the embedding matrix. This matrix has a single column for every one of those 50,000 tokens in the vocabulary, and in GPT-3, each one of those columns extends down 12,288 rows. You can think of this matrix as a massive lookup table. It grabs a discrete piece of text and maps it to a continuous vector, a set of coordinates in a 12,288 dimensional space. This 3D graph visualizes a slice of that massive embedding space. As the model learns, it organizes vectors so physical direction carries semantic meaning. If you start at king, subtract the vector for man, and add woman, the math drops you almost exactly on queen. The embedding matrix translates the abstract concepts of language into fixed, measurable locations. Once words are turned into vectors, the model needs a way to mathematically evaluate their similarity. It does this using the dot product. The dot product quantifies alignment. When two vectors point in similar directions in the embedding space, their dot product yields a high positive value, indicating a strong conceptual link. But an isolated embedding only captures the baseline definition of a single word. It lacks context. The word model means one thing in fashion and another in machine learning. To gather that surrounding information, the network processes a fixed block of tokens simultaneously, known as its context window. For GPT-3, this is a sequence of 2,048 tokens. The data physically flows through the network as a rigid array of 2048 vector columns, moving forward in parallel. These vectors pass through alternating attention blocks and multi-layer perceptrons. These hidden layers allow the vectors to communicate back and forth, updating coordinates based on surroundings. By the pipeline's end, our focus shifts entirely to the final vector. The entire purpose of the hidden layers is to bake the semantic context of the full passage into the coordinates of that single final vector. Now the system has to translate this single context-rich vector back into text to predict the next word. This introduces the final set of weights, the unembedding matrix. The 12,288 dimensional vector is multiplied against the rows of this new matrix. The output is a single list populated with 50,000 distinct numbers. In machine learning, these 50,000 raw output scores are called logits. Each acts as a score for one possible token. But because they are the direct result of matrix multiplication, the raw output is messy, filled with negative numbers and values vastly greater than 1. This is a problem. You cannot use negative numbers to represent a probability distribution, which means the model cannot yet use these scores to make a prediction. The network has successfully generated a mathematical score for every possible next word, but these logits must be compressed and normalized before the system can actually select a final output. To fix the logits, the system runs them through a compressor called the softmax function, which converts the raw scores into a valid probability distribution. First, it raises e to the power of each logit, forcing every value to become positive. Next, it divides each term by their total sum. Now every value falls between 0 and 1, and the list adds up to exactly 100%. The nature of exponentiation means the largest original logit aggressively dominates the final probability distribution. Engineers can manipulate this shape using a mathematical parameter called temperature. Set the temperature to 0, and the maximum value consumes all the weight, making the output completely deterministic. But increasing the temperature flattens the distribution. Lower probability words gain weight, allowing a model to select less obvious words and generate more creative text. Once the probability distribution is finalized, the system takes a random sample based on those exact percentages, locking in the next token. And here is where the model achieves auto-regression. That single, newly generated token is instantly appended to the end of the original input sequence. To generate a sentence, this entire pipeline of matrix vector multiplication must start over from the very beginning, processing the updated context window to predict the next word. Text generation contains no intuition. It is simply a relentless, looping cycle of continuous geometric transformations and normalized probability distributions.